Today, we're taking a plunge into a truly fascinating area where expert knowledge meets data-driven learning. Fuzzy-informed neural networks, or FINs.
It's a really interesting concept, yeah, that tackles something fundamental, that not everything in human understanding fits neatly into, like, crisp equations.
Absolutely. And, this field owes a lot to some key work like the article Perception-Informed Neural Networks, Beyond Physics-Informed Neural Networks. FINs were a really central idea there.
That's right.
And one of the co-authors, Dr. Moran Mazandarani, we were really hoping he could join us today. Unfortunately, he's down with a cold.
Oh, that's a shame.
Yeah, we're definitely wishing him a very speedy recovery. His contributions have been significant.
Indeed. He and his colleagues really helped shape this powerful approach.
So our mission today really is to get a conceptual grip on these FINs. What are they? And maybe more importantly, how do they actually use this inherently fuzzy information to guide how a neural network learns?
Okay, yeah, let's unpack that. To sort of set the stage, you might have heard of physics-informed neural networks.
Right. They build in known physical laws, often as equations, right into the training alongside whatever data they have.
Exactly.
Which is great when data is scarce, I suppose. The physics helps guide things.
Precisely. But the real world, well, it's often messy, isn't it? You've got uncertainty, vagueness, expert knowledge that just doesn't boil down to a neat physics equation.
Like when an expert says something needs a bit more adjustment or feels about right, that's not really an equation, is it?
Exactly. And that's where this broader idea comes in perception-informed neural network. PRINs, they were developed to extend PIN to handle these more flexible types of perception-based information.
So not just fuzzy logic.
No, it's broader. It could be fuzzy or probabilistic, maybe interval representations. Basically ways to capture knowledge that isn't strictly crisp.
Ah, okay. So PRINs are the big umbrella for imprecise knowledge, and FINs are a specific type under that.
That's the idea. Fuzzy-informed neural networks are a special subclass. They're specifically designed to handle knowledge expressed using fuzzy logic.
Yeah.
Especially those familiar fuzzy if-then rules.
Got it. So the core idea isn't just that FINs know about fuzzy rules, it's that they actually bake them into the learning process itself.
That's the absolute key point. Fuzzy-informed neural networks integrate these fuzzy if-then rules directly into how the neural network is trained. The goal is combining that qualitative expert fuzzy knowledge, that human intuition.
The imprecise stuff.
Right, with a quantitative data-driven learning.
Okay, blending that qualitative know-how with the quantitative data. Interesting.
It's a really neat combination.
All right, let's unpack the how.
Well, think of it like adding a special kind of guiding force during the network's training. It really starts with getting that human expertise down.
Okay, so step one. Capturing expert knowledge as fuzzy rules.
Right. You start with experts providing their knowledge, often in areas like control systems, as these simple if-then rules. Like if the error is small and de-error rate is near 0, then the control output should be medium.
So rules that describe how the system should behave qualitatively.
Exactly. They capture those desired relationships. So you collect a set of these. Then step 2.
Step 2 is translating each rule into a soft constraint. Is that right?
Yeah, essentially. Translating those fuzzy rules into, well, soft constraints. Each rule suggests a relationship, a joint constraint.
Okay.
And we quantify how well the network's current state and output match that rule, usually using something called a T-norm, often just the minimum function.
So you check how much the input fits kind of low and how much the output fits mostly closed and take the minimum of those.
You got it. That gives a value between 0 and 1, representing how well that single rule is satisfied right now.
A satisfaction score for each rule, basically.
Yeah, essentially. Higher score means better alignment with that specific rule. But systems usually have lots of rules. Step 3 is aggregating all rules.
Right, into a total restriction. You need one overall measure. How well does the network's current output align with the guidance from all the relevant fuzzy rules combined?
How do you combine them?
Using an S-norm operator often that's the maximum function. It takes the results from all the individual rule constraints and aggregates them.
Into a single number.
R.
Between 0 and 1.
Yep, that's R, the total restriction. If R is close to 1, the network's output fits the combined fuzzy rules well. If it's near 0, it's violating them.
And this R value is the magic ingredient for training. Step 4, incorporating the fuzzy constraint into the loss function.
This is really the heart of the FINN approach, based on the source. You create a new term in the network's loss function. It's not just about matching data anymore. What's the core idea here, according to the source?
Well, the paper explains they create a specific dedicated loss term. They call it L sub R for rule. And its whole job is basically to penalize the network if its outputs don't align with the fuzzy rules defined by the experts.
Okay, a penalty, just for the fuzzy part. How's that calculated? What's the formula they use in FINS?
The formula for L sub R is given as M multiplied by the square of 1 minus R.
M multiplied by the square of 1 minus R. Okay, sounds specific. Let's break that down. What's the R in that?
So R is this value between 0 and 1. It represents how well the network's output actually satisfies all the relevant fuzzy rules together. If R is 1, it means perfect satisfaction.
And if R is 0?
Then it completely violates the rules. And, values in between mean partial satisfaction.
Got it. So if R is 1, perfect satisfaction, then 1R is 0. Square that, it's still 0. Multiply by M, 0 penalty. Makes sense.
Exactly. No penalty if the rules are met. But if the output violates the rules, R gets closer to 0. So 1R gets closer to 1. You square that, it's still close to 1. Multiply by M, you get a penalty close to M.
And M, what's the role of M?
M is just a coefficient, a weight, basically. The user sets it, usually 1 or more. It controls how much emphasis is put on satisfying the fuzzy rules compared to, say, fitting the actual data. A bigger M means violating rules is more costly during training.
Right. So you calculate this L sub R penalty based on rule satisfaction. And then step 4 says you just add this L sub R to the regular loss function, the one that measures fit to the data, maybe call it L sub D.
Precisely. The total loss that the network tries to minimize becomes L equals L sub D plus L sub R.
Ah, okay. So the network is learning to do two things at once.
Yes. It's trying to fit the quantitative data and simultaneously trying to make its outputs consistent with those qualitative, fuzzy expert rules. It balances both.
And that addition, that L sub R term, that's the key. It makes the fuzzy rules an active part of training, not just an afterthought analysis. It's like a soft constraint.
Exactly. It incentivizes the network to follow the rules rather than forcing it rigidly. This is really what lets the FINN learn from both streams, the data and the expert intuition encoded fuzzily.
It's a pretty powerful idea, merging qualitative insight right into the learning model's core objective.
The source uses a control system example to make this concrete, right?
Yeah.
Using error and error rate.
Yeah, it's a classic application. Inputs like system error E and the rate of change of error determining some control output U.
Like if error is negative big and error rate is negative small, then output is negative big rule we mentioned.
Exactly. And the material notes there might be, say, 25 such rules for a typical controller, covering different combinations of error and error rate.
So for any given E and error rate, the network predicts a U. Then the system calculates the membership values, combines them using T norms and S norms to get that overall R value.
And then calculates the total loss, L equal LD plus LR. LR penalizes violations of those 25 expert rules.
And training minimizes this combined loss, pushing the controller to be effective and behave according to the expert's logic.
Precisely. And here's a really interesting point the source emphasizes. Because of this structure, FINs can potentially be used in real-time control without massive amounts of pre-training.
Wait, really? Neural network controllers usually need tons of training data or simulation time. How does adding fuzzy rules skip that?
Because that fuzzy loss term, LR, acts as a strong initial guide. It's like giving the network a cheat sheet from the expert right from the beginning.
Right.
It tells the network roughly how it should behave in different regions, which drastically reduces the purely random exploration phase needed otherwise.
That makes sense. It's like starting with a rough map instead of wandering completely blind. That's a huge potential advantage.
It really is, especially for systems where extensive trial and error learning is risky or expensive.
And that allows for real-time fuzzy control, online training, online inference. So, stepping back, what are the key takeaways about the fuzzy-informed neural networks? What really defines them?
Well, first, encoding expert fuzzy rules as constraints directly in the loss. That's fundamental. Second, this principled way of balancing data fitting with satisfying those qualitative rules.
And the source mentioned something about defuzzification.
Ah, yes, a big one. It explicitly states FINs require no defuzzification step. In classical fuzzy systems, you convert the fuzzy output back to a crisp number. Skipping that simplifies things a lot.
And you highlighted a big practical plus. No defuzzification needed.
Yeah, that's huge compared to traditional fuzzy systems. Defuzzification, turning the fuzzy output back into a single crisp number, can be complex. FINs just output the crisp number directly from the network.
So simpler implementation, potentially faster online operation,
Definitely.
which enables that real-time online learning capability.
Exactly. It makes them function more directly as a real-time fuzzy controller. Another point is flexibility. The source says you can apply this fuzzy loss term to any deep neural network architecture.
You don't need to rebuild the whole network, just add the loss term.
Conceptually, yes, you modify the training objective, not necessarily the network layers themselves. Because the fuzzy part is in the loss function, you can use this fiends approach with pretty much any deep neural network architecture.
You're not locked into a specific network structure.
Nope. Use a CNN, an RNN, a transformer, whatever fits your problem best. You just add the LR term to your loss. This is quite different from something like ANFIS, which has a more rigid structure tied to the rules.
That's a significant difference. It makes it easier to adopt.
It does. And it also makes implementing different kinds of fuzzy logic, like type 1 or even type 2, potentially simpler because you bypass the hard parts of their traditional implementation, like type 2 defuzzification.
And the online training capability is another key feature.
Yes, the ability to learn and adapt in real time, guided by the rules and incoming data.
Does adding these rules help the network in other ways? Maybe prevent weird outputs?
Absolutely. The fuzzy constraints act as a form of regularization. They guide the network away from solutions that might fit the data points perfectly but make no sense according to the expert rules, especially outside the range of the training data.
So better generalization. Less likely to give crazy answers when faced with new situations.
That's the idea. It helps make the network's behavior more reasonable and aligned with known principles or expertise.
So we've talked about how they work, the steps involved, the control example, the advantages. Bringing it back to the listener, why should you care about it? Fuzzy-informed neural networks. What's the real-world relevance?
Well, think about it. So many real-world problems involve uncertainty, vagueness, or rely heavily on human expert knowledge that isn't easily written down as a precise equation.
Right. Medicine, finance, complex system control.
Exactly. FANs offer a way to actually use that valuable, sometimes imprecise human insight directly within powerful learning machines like neural networks. If you're working on a system where you have expert rules of thumb, but maybe not mountains of perfect data,
Or the data is noisy or incomplete.
then fiends give you a tool to leverage that expertise, to handle the imprecision, and potentially build more robust, reliable, and frankly, more intelligent systems.
It's like teaching the network to understand not just data points, but also the reasoning, the gut feel, expressed as these fuzzy rules.
That's a good analogy. It bridges that gap between the qualitative human world and the quantitative machine learning world.
Okay, so to recap, we've explored fuzzy-informed neural networks.
Fiends.
We saw they're a type of perception-informed network that specifically embeds expert fuzzy if-then rules right into the neural network's loss function.
Which lets them learn from data while also respecting that qualitative expert knowledge, balancing the two.
And key practical benefits include avoiding defuzzification, architectural flexibility, and the potential for online learning and better generalization.
It really is a neat way to combine different kinds of information.
So here's something to think about as we wrap up. What new possibilities open up when our AI systems can learn not just from data sets and physical laws, but directly from human perception and intuition, expressed as these inherently imprecise, fuzzy rules?
Yeah, how might that change how we design intelligent systems, especially in really complex domains, maybe healthcare, autonomous systems, process control, where human judgment and experience are absolutely critical?
Could we build systems that collaborate more deeply with human experts, learning the nuances of their wisdom? Definitely food for thought. Thanks for joining us on this deep dive.